I'll give it 4 minutes and see if people arrive. Did anyone note that we're supposed to be online this week? Sorry. I realized on Saturday morning when I read the email that I'd sent out at midnight the previous night that we were doing that. So I shifted it. So if you look at the syllabus later in the semester, you get your time not listening to me, but listening to me online. But we just shifted it. So irrespective, the 5 extra credits come. So it's not going to be linked to number, 0.3% times the number of times. It's just going to be a straight 5. So it doesn't really affect things. In fact, it's probably better if you don't have to do the stuff online because you still get the 5% for what you put in so far. So originally my plan was that I was going to be a thesis defense at USC today, a project proposal review meeting in DC for DOE tomorrow, a meeting in Palo Alto on Thursday and Friday for review of a big project. I think in Beijing over the weekend, in Amsterdam on Tuesday for another meeting, and then in China again the following weekend. So unfortunately, due to COVID and due to Zoom, I actually don't get to go to any of these places anymore. And so it's all, so those things are still happening, but I'm physically not going to be there. I wasn't going to be there anyway, really, but I was just attempting to free up the schedule a little bit for that. So it doesn't matter. I did think also about switching week 9 and week 8, because week 9, well, it'll be next week when we don't actually do it, because we're doing the midterms. But week 9 is on dimensional analysis, which is actually a kind of a neat tool, and it's just different from this conservation stuff that we've been doing so far. But anyway, so I decided not to do that, just to not confuse anybody. So what I did was I took the credits for this week when you've been doing it online and placed it sometimes in November. You'll see that on the syllabus, it's updated. And so we'll carry on with this then. So thanks for coming, despite my snafu. So week 8, we've talked about 6, 7, and 8 being conservation weeks. 6 was conservation of mass, which is just the same as volume in equals volume out on a streamline that we use for Bernoulli. Week 7 was conservation of momentum, which was just the main part of Bernoulli, the 3 components, elevation head, pressure head, and velocity head, the v squared over 2g terms on each side of the equation. And so conservation of momentum is just exactly that, F equals ma, but in a random geometry and allowing things like moving control volumes, which we talked about. And so today is the final conservation of energy, and it's conservation of kinetic energy, half mv squared, essentially. And the reason that we're interested in that is because sometimes within these systems, we're interested in things which are not conservative in an energy sense. So certainly Bernoulli is only for inviscid fluids, and so there's no physical frictional losses in the system. The example of pulling my bag across the table and then pushing it back to where it was before, it loses energy on the time pulling it, and it loses energy on the time pushing it. I guess that's an earthquake on the screen above. And so now when we talk about energy, we want to be able to account for the fact that in real flow systems there are frictional losses, which we have to account for. So that's one of the things. And also in energy systems there are inputs into the system which are different. They could be chemical inputs, for instance an internal combustion engine or a turbine when you're burning gas. We won't really talk about that very much. Or it could be hot water that comes into a system, as in a geothermal project. You bring it up under high pressure, high temperature, and then when it's on your surface, you allow it to flash to steam, so it goes through a phase change. And that input of energy into the system is the mechanism by which you drive the turbine, which you generate electricity from, you condense the water, you send it back into the reservoir, etc. And so that's kind of what's running here. And actually, this is perfect, because 5 minutes into this is where it starts talking about this new geothermal system, which is kind of interesting. It's called Ever, I think it is, if you pronounce it the way. And conventional geothermal systems are in the geysers in San Francisco, near San Francisco in the Bay Area. It's a plate boundary, it's hot, at shallow depths. There's lots of motion because of earthquakes in the crust, so the crust is broken. And so you can circulate fluids through a big geological heat exchanger. You bring out hot fluids, you flash them, you re-inject them as cold fluids. You could even inject cold fluid and heat it up in the geological heat exchanger and bring it back to the surface. And that's fine, but of course that's only close to one part of population. The east coast of the US has no hot surfaces near the surface, and so the holy grail would be to have energy produced at source, underneath New York City, underneath State College, where you actually use it. And this system is called EVER. It's kind of an interesting take on it. It involves kind of improvements in drilling. So you drill down, you drill directionally horizontally, you drill directionally a long way horizontally, maybe 5 kilometers. So here to Bowlesburg, where I live, for instance, is that kind of distance, quite an amazing distance. You case it all the way. You join the casing somehow magically in their trademark method underground, and then you drill a whole bunch of laterals. And so it's a bit like a heat pump, a ground-sourced heat pump, where you have all these coils buried maybe 3 or 4 meters below the ground, which take the constant heat from the ground, which is about 55 Fahrenheit, 10 degrees centigrade, to be able to cool in the summertime and warm in the wintertime. They're a heat source. But this is doing exactly the same thing. It's a closed system. The fluid in the system never goes out of the drill pipe. It relies on conduction from the rock into the drill pipe, which is actually quite a slow process. So I'm kind of curious as to whether this really works or not. Maybe it works because the laterals are just so long. So a heat pump system works well because these coils of tubes, which you'd have seen earlier on in the video, are long. Maybe there's a kilometer of tubes, it just happens to be coiled, and so the residence time of the water in there to be able to get the heat is a long time. And so you can get these deeper and you can get hotter as a result. So there is a prototype of this. They showed it with the snow. It's in Rocky Mountain House in western Alberta, between Calgary and Edmonton, but closer to the Rockies. This may be the site actually that they're talking about. And so they bring up hot water. Sometimes you could use that hot water in a heat exchanger to heat buildings. Like on campus, we use natural gas. We did use coal. We now use natural gas at the steam plant on Burroughs and College. And heat water, which is used to heat the campus in the wintertime and to chill the campus in the summertime. Or you could use it to generate electricity if it's hot enough. And so if you bring up water, which perhaps is only so this is how it works here. So you bring up water that has some temperature, you put it through a heat exchanger, and potentially that heat exchanger, if I stop it here, oops, I don't want to do that, is you heat up a fluid, and so you have a binary system. So the fluid within the turbine is not steam that you flash, but it's maybe something like isopropyl alcohol, which has a boiling point of only 40 degrees centigrade. So water has 100 centigrade, IPA has maybe 40. So even cool water coming out of the subsurface can flash that fluid from a liquid to steam, to gas, goes through a turbine under the expansion. The expansion then takes it to the other side of the turbine, it's cooled, and then it's used again in a continuous closed loop cycle. And so that way you can use water that is less than 100 degrees centigrade to be able to generate electricity, because all of our ways of generating electricity involve phase changes. So that's kind of what we're talking about today. So that's kind of an application of that. And so when we talk about conservation of energy in that form, we're allowing for the fact that we can input energy into the system. There's physical changes in the system. It's relatively straightforward. We could do it in a very complicated way. I'll try not to do that because I'm never sure that that's a particularly useful way of doing things. So, interesting movie anyway. So EAVOR is the company, and so they're a new startup with a new idea. They have a prototype, so they must know whether it works or not. I think for me that whether it works or not hinges on whether you can conduct heat quickly enough to these pipes which are transmitting fluid through them, water through them, and I'm not sure whether that's the case or not. So I've never seen their data. So anyway, so that's kind of our pathway to today. So what are we going to talk about? What do we want to talk about? All right. So to set the stage, they stole my table, but we'll see if I can work here anyway. You'll remember that we used Reynolds transport theorem, kind of sparingly. Remember that what we used before was that we used this term, which is substituted through here. In week 6, we had this was equal to conservation of mass. And we basically came up that conservation of mass plus the other terms was equal to 0, right? Mass in equals mass out, and then there's some accumulation terms. This was 6. So week 7, then this term was equal to momentum. And we came up with what? Sum of forces is equal to sum of velocities times mass flow rates, and some derivatives on this. And so now, we're not going to derive it, but now we'd like to include the fact that B is now essentially equal to mass times velocity. So this is equal to, we could write it if we wanted to, as half mv squared, something you're already familiar with. And so we're going to conserve this. Remember that lowercase b was just mass per unit volume, so you just divide out this mass term from it. The units of this are going to be what? Kilograms, meters per second, meters per second. And so meters per second squared would be this. So this is kilograms, meters per second squared. 1 kilogram, acceleration of 1 meter per second squared is a definition of Newton. And multiplied by this is a meter. So by definition, this is joules, right? We're typically interested in, ultimately, in looking at not mass, but mass rates. And so if it's a mass rate, say dot v, then it's just going to be a joule per second. This is just, instead of being kilograms, now this is kilograms per second, meters per second. So we divide this, and this, of course, is a watt. Named after George Watt, right? From Scotland. He was born in the same city I was born, Glasgow. And so what we can do with this, I'm not going to do it, I'm just going to go to the result, is that maybe we can also think of this term that we add into Reynolds transport theorem as it ends up being something a bit more than kinetic energy. We can write the B term as equal to something a little bit different. And B could be equal to mass, as we had before, multiplied through by internal energy per unit mass, V squared over 2, plus GZ. And so this we can think of as being equal to EM. This is the mass. This is E. This is the energy, if you like, in the system. So this term here is equal to enthalpy plus pressure over rho, rather, I think, right? Pressure over density. No, other way around. Sorry, I messed up. Enthalpy is equal to internal energy per unit volume plus P over rho. This is a pressure. And so you see that in this term we've got the velocity squared term, we've got the elevation head, we don't have the pressure head, so it ends up going into this particular component here. If it does that, it must reboot at some particular time, see if it's 20 after. And so anyway, so if you substitute this in and do some manipulation, you end up with two potential equations, and I'm not going to do the derivation. You'll see that if we wanted to, we could talk about this forever and end up with the same place, and I don't think that's very fruitful for us to do it. I would just like to make the case of what we end up with. So we end up with two different equations. The first one is this, which we will use. They're both kind of Bernoulli-esque, and the second one is this. And so I'm not sure what the best way to look at these expressions is. Best way maybe is to just think about drawing a diagram. So the diagram is this. So we've dealt with streamlines and stream tubes before. And that's all I'm drawing here, is that we have maybe an upstream and a downstream location. We've always called them 1 and 2 from upstream or downstream. It actually didn't matter in anything we've done so far. But this would have a velocity V2, it would have a pressure P2, it would have an elevation Z2, and this would have the same here, velocity V1, pressure P1, elevation C1. We could draw some kind of datum, I guess. And we know that if we do this, and I'll use color codes for this, that this here would be Z1. This here would be Z2. We could, what else do we know? We could have, let's say the pressures were equal upstream and downstream, just for the heck of it. I'm going to change the colors. So this then would be P1 over unit weight. This would be P2 over unit weight. And then if we have a velocity, we know that if the diameter of this pipe doesn't change from upstream to downstream, then we also know that these two terms have to be equivalent to each other. So that's what we've done so far. So if we look at Bernoulli, and I make it a bit smaller, see if I can make it smaller. You see they stole my chair, my table today. So this is Bernoulli written between upstream. I guess we've done it. This is perhaps not. This is the one side is this side. I don't know why I wrote it backwards. So this is the pressure in, P1 over unit weight. This is V squared over 2G multiplied by alpha. We've always assumed when we look at flow within a tube that the velocity within that stream tube has always looked a bit like this. We've always been able to get the total flow rate just by multiplying the velocity by the cross-sectional area. So Bernoulli assumes that this is the profile. The reality is if you're flowing fluid within a tube, the velocity profile will look like this. It'll be a parabola. And the reason for this is because we know that from Newton's law of viscosity, dvx dz. So let's have this as the z direction. The change of velocity in the x direction, horizontally, as you go across it, is no longer constant. And we know that because of that, because when we talked about plates where we had viscosity applied, we'd attach the fluid to one plate, so the velocity at the plate would actually be zero velocity. So it can't be this if there's viscosity occurring. So this is for the case when viscosity is zero, and this is the case when viscosity is not equal to zero. And so to account for this, that's what this extra term is, alpha, that includes here. So alpha is equal to 1 for this, and alpha is just less than 1 for this. And so we probably won't worry about that too much, but that's the reality. And so that happens when we have really true viscous fluids. And so we have pressure 1, velocity 1, and elevation 1. And this is what they look like here. And we also have this term here. So this allows us, this is the pump head. This allows us to put energy into the system. And so the reason I drew this diagram is because it allows us to perhaps show exactly what this is. And so this would be on the upstream side. So let me also write this as, this is the upstream. So now it's important which is upstream and downstream. This will always be on the upstream component. And this has to be units of length because it's the same, we're adding apples to apples. And so this is equal to the amount of energy we put into the system. And so HP equals pump head. Again, it has a sign convention. It's positive if it's a pump. You're putting energy into the system. And it's negative if it's a turbine. So you're running water through it at speed to be able to get stuff out at the other side. And on the other side, we have these other terms. This would be P2. So I guess this is downstream. And we have another term here, which is head loss. And I guess I'm going to modify this slightly. I'm going to take the tail off this and have it only pointing upwards, because as you'll see in a second. And so the other thing is that this is the loss. I guess I do. And so the reason for doing that is that these two sides are equivalent to each other. And so that means that the stack of these terms on the left-hand side has to equal the stack on the right-hand side. That second term is a head loss. And it's always positive. In other words, it's always a loss. So the same idea as this. If I'm pulling this across the table, I lose energy pulling it to me. I lose energy putting it back to it. So it's always positive. It never changes sign. And so this allows us to define a couple of things. We can define what we call an energy grade line. And we can, which is EGL by terminology, and a hydraulic grade line. So HGL, if you like. I know I'm using up too much space. And the hydraulic grade line just includes all the terms of regular Bernoulli. The difference between those and the energy grade line is this. And I suppose we could think about it, maybe I'd like to draw a nice thick line, or a thicker line, is that you could imagine having a line that does this. So this is really the energy grade line as it comes across. So in other words, we put some energy into the system to push water using the pump. The pump head has some energy attached to it. It's a length, but it represents energy, the power that we're using. And it adds some extra pressure, effective pressure upstream, that's pushing the water downstream and having it push against the magnitude of the losses. So the losses really would be due to, I guess I could make this small again. Don't know why I worry too much about that. But the losses would be viscous losses on the inside, if you can think of this as being a shear stress. This is shear stress. So you could imagine also if you have to apply a bigger pressure upstream to get it downstream, say you were pumping fluid out of here and it was coming out at atmospheric pressure, then the pressure would be zero, then there'd be a pressure loss across here, and that would just be due to this shear stress acting. So in other words, you could quite simply from Bernoulli, too blunt an instrument, I guess, I didn't make it quite unblunt enough. So you could imagine that P1 minus P2 over, actually, let's keep it as a pressure, multiplied by an area. Area would be the area, the cross-sectional area. A pipe has to be equal to tau times 2 pi r L. You don't need that equation, but you can see what this is. This is an area. A shear stress multiplied by an area is a force, and this force is just countering the force is the loss. And so the very real force that you have to act against in any pipe flow problem is against the viscous resistance to flow in a pipe. It's there for water. It would be obvious, right, if it was treacle that you're trying to push along a pipe, or molasses, you'd have to apply a pressure upstream to be able to use it. So that's the first equation that we'll use. The second expression, and so the other thing that is related to this, since the pump head and the head loss, I guess we've talked about the head loss. This is kind of the head loss. This would be kind of the head loss. Let's not worry about it for now. But the more important thing is that we can also define the pump head. And these, so equations 1 and 2, we haven't got to equation 2 yet, but equation 1 includes this term for the pump head. The pump head is defined as this. And so this is in terms of the shaft work in. So you're putting work into it, you're turning the pump, and you're putting energy into it. So this is the shaft work per unit mass. And this is G due to gravity. And actually an easier expression to use is just to substitute this shaft work in is equal to the power, the rate of doing work in the system, divided by the mass flow rate. So I'm just going to write those two. So the pump head you can define as being equal to the shaft work. An unfortunate term, this isn't the W velocity we've been using, this is watts, divided by what we've called mass flow rate times G. So this is an important expression. This is the best way to write it. And again, if we wanted to, I guess we could make sure that it's in the right units, but perhaps you can do that yourself. This is watts, so W is equal to joules per second, which is equal to Newton meters per second. The dot just is rate of doing work, right? This is work, this is rate of doing work, so hence the dot. So that's it. So if we know what the power of our pump is and how much pumping we're doing, we can calculate the rest of our equation, hopefully, if we know it. And what else do we need to know? Nothing. We don't need to know about head loss now, except for this sign convention. This sign convention, I guess, is important. I apologize for overstepping with the energy grade lines, etc. So that's the first expression. So the second expression, again, is kind of written the same way. I should probably clean it off a little bit. I don't need to, just to get some stuff out of the way. And that is that you've got it captured on video. So the other way to write Bernoulli, so this is the first expression that we had. The second form of Bernoulli, again, it's just a linear form, and it's between upstream and downstream components. But now we have two other components. This is the work, power, I guess, rate of work, going into the system. In other words, power in, that's an R. So this is how much, this is the same as the pump head that we're putting into the system in this equation here. And this is a slightly different expression. This is the thermal energy that's going into the system. So this is thermal energy in. So potentially you can balance the systems. What we've done so far is we've looked at kind of ideal gas laws, adiabatic ideal gas laws, where this has been insulated. There's no actual net thermal energy in, but it allows us to be able to accommodate that. And now this is written slightly differently. So Bernoulli, before we had both the elevation head and we had the velocity head. So those still exist, elevation head and velocity head, v squared over 2g. But we're missing this expression here. And so in this particular form of the equation, we won't derive it. We use enthalpy to be defined as the internal energy per unit mass divided by the pressure head energy. So in other words, this term that we have here is embodied in this, and this is enthalpy plus internal energy per unit mass plus P over density of the fluid. No, that's not an equals, is it? And so this form of the expression is useful when we have not only stuff coming in at a different pressure upstream to downstream, as we said we might have here, right? If the pressure upstream is larger than the pressure discharging, then that has to be eaten up somehow if, for instance, we're at the same elevation, and certainly if the pipe is at the same diameter from upstream to downstream, because the velocity can't change from upstream to downstream. So if P is large and this is 0, because it's atmospheric, then this has to be worked again by some kind of loss. And that loss is going to be the friction in our system. So that works out fine in terms of dealing with this expression here, in that we can allow for pressure. But what if we have something coming in with a lot of thermal energy in it and going out cooler because we've changed phase between the upstream and downstream? Well, we can account for that by this enthalpy term here, which includes both the internal energy in the system multiplied and added to it the pressure in the system. So enthalpy would be, so enthalpy is equal to internal energy per unit mass plus pressure over density. And so the units of this have to be the same, and so enthalpy will be in units of joules per kilogram. I'm pretty sure. And so we have to be able to account for that. And so, yeah. And so if we take joules per kilogram, let's see if this is right. So mass rate times enthalpy in terms of units will equal kilograms per second multiplied by joules per kilogram. And then this comes out to be joules per second, which is equal to watts. So at least it's homogeneous. So those are the two forms of the expression that we'll use. And so they're there for your utility. This rate of doing work is the same as this one here. And so everything we've talked about in terms of their behavior follows directly from that. So that's it. So we've avoided, if you like, endless pages of derivations and rationalizations, and I'm just going to do a couple of examples, straightforward examples from the book. And one is involving the first equation. No, sorry. The first is one is involving the first equation. One is involving the second equation. This one is involving the second equation, and you can see the description of it here, relatively straightforward. So you have steam coming into turbine. It comes in with a particular velocity in terms of meters a second. It has an incoming enthalpy of 3,348 kilojoules, joules per kilogram, kilojoules. This is 3,000 times 10 to the 3 joules per kilogram. It comes out from the system as a mixture of liquid and vapor. It comes out at a different velocity because it's expanded. It's gone through a phase change, and it now has a reduced enthalpy of 2550 instead of 3348. It's adiabatic, so that means that Q dot is equal to 0. Q dot net in, we called it, is equal to 0. And so you can just define these things on this system. You define a control volume. You only have stuff coming in on one side and leaving on the other side. You know the velocity it comes in at. You know the enthalpy it comes in at, which includes the pressure. So pressure is included in this, right? Enthalpy is equal internal energy plus pressure over whatever the local density of the fluid is. So this density obviously is changing if it's going through a phase change from liquid to vapor. And so enthalpy allows us to get around that problem by having a coefficient that includes intrinsically that phase change. And if we look on the downstream side, we have velocity coming out faster than it went in, and the enthalpy is reduced. And so the expression, this is our equation number 2. Mass flow rate, kilograms per second, enthalpy in minus enthalpy out, enthalpy, velocity in minus velocity out, divided by 2, elevation, I suppose, C2, C1. So we lose those terms. So these terms drop out. It's adiabatic, and the only thing we're left with is how much shaft work do we get out of it, presumably, right? Because it's going in at high enthalpy, it's coming out at low enthalpy. Presumably we're getting work out of it. And so what we could do here, which is useful, the question is how much work output per unit mass of steam. And so that is our lowercase w. So we want W, and you know the expression, if we go back, we had it up here somewhere, this term here. So this, I guess it's this term here. So this is work per unit mass of fluid that's going through the system. And so the easiest thing to do is to just divide both sides of our equation by mass flow rate. And that's exactly what they do. So what we can do is we can divide this by m dot. That gets this divided by m dot. And then this is, by definition, equal to lowercase w. So this is lowercase w dot. And it comes out, if you do the math, that we have the enthalpy in, enthalpy out, velocity in, velocity out. They go through the math. And it comes in that the shaft network is equal to, it would be negative, because this is a 30 times 1, and this is a minus 60 times 1. So this is negative, and this would be W net in from this, right? Shaft net in, so it's W net in. But because it's negative, that means you're getting work out of it. The sign matters. So I guess I probably didn't say it when we were talking about it. So for W dot net in is positive if you're putting work in, and it's negative if you're getting work out. So work in would be a pump. This is like pump head. This is equivalent, but different units, to pump head. And this is also pump head. Different units, but you get the idea. So in other words, we were able to calculate the amount of power we get out of this, because this is a rate of doing work per unit. So I guess in terms of units, it would be W stop it. W small is equal to W over mass flow rate. And so it would be the watts per kilogram per second, right? This has to be watts. And mass flow rate has to be kilograms per second. So it's watts per kilogram of steam into the system per second. So pretty straightforward. So that's just one exposition, if you like, of using this, where we're getting enthalpy coming in. So we had no way of doing that, of course, before. When we're just using, if we were just to use Bernoulli, we have no expression that allows us to accommodate the fact that fluids are coming in either chemically charged by their phase state or charged by their chemical potential. If you burn something in a combustor, such as natural gas coming in, combust it, CO2 comes out, then that transformation can also be taken care of as a change in enthalpy from upstream to downstream, and so you'd have to use an expression that includes enthalpy. If you don't have a phase change or a chemical reaction in the system, then the equation that we'll use almost exclusively in this class, except for this one example that we just did, is to use Bernoulli in this form. And so this first equation will pervade everything we do from now on, because, well, we'll do with dimensional analysis in week 9, but in week 10 and 11 we'll talk about flow in pipes. And the essence of flow in pipes is that there's a loss due to frictional resistance along the pipe that we have to overcome. And typically we overcome that by having a pressure upstream that drives the flow. When you send gas from Louisiana to Pennsylvania or to New York City, you have to have an upstream pressure to get it to go there, because it's roughly horizontal, because gas lines are underground, shallowly underground. And so you have to apply a pressure to be able to do that. And you apply that pressure by pumping it. You have compressor stations along the length of the pipeline to be able to do that. And so the other thing that we can look at is being able to look at this expression to describe behavior. So the other example that we'll quickly, well, not so quickly, we've got 10 minutes, is this one, again from the book. And for this, we can use our expression number 1. This is just our straight Bernoulli, if you like. And it's really kind of showing the obvious, if you think about it. And that is, if you have a pump storage scheme, so one of the big problems, especially in this non-dispatchable new energy world of wind and solar power, is that you only get wind when the wind blows, and you only get solar power when the sun shines. And so the sun doesn't shine at night, so you want to store it. You can store it on batteries. Batteries are expensive and not really grid scale necessarily. And so one thing you can do, which has been around certainly since the 1970s, are pumped storage schemes. That's half a century. And that is, at night time, you take a lower lake, you pump water up to an upper reservoir. When the electricity is cheap, nuclear power you can't turn off at night. And then when you need the power in the morning, you let it run back down through the turbine, and you get some energy from it. And of course, you know that there are no perpetual motion machines, so you always lose energy within a system. And so what is that energy in terms of Bernoulli in this particular case? So you can think, I guess, in terms of the turbine cycle. And so when you're running it down, so the turbine cycle, you would run it down between upstream and downstream. You have the pump head in the middle. Perhaps I could draw it actually on the thing like we've done before. You have pump head on the middle. And so we can write Bernoulli in terms of our usual one, Z1 plus P1 over gamma plus V1 squared over 2G plus HP minus Z2 plus P2 over unit weight plus V2 squared over 2G plus HL. And so most of these terms are going to disappear. Pressure in the upper reservoir is 0, atmospheric. Pressure in the big reservoir downstream is 0. Velocity, big lake assumption, means the velocity of this surface is 0 as well. So we lose that. And the lower lake as well. So we're left with only Z1 that's equals, not minus, Z1 minus Z2 plus HP equals minus HL. And so I guess we could write this, I'd like to write it the other way around. In terms of the pump head, this is the power that comes out of the turbine is equal to Z2 minus Z1 minus HL. Z2, why is that backwards? So this is, okay, this is negative. And so this means that this is negative because this is now not pumping, this is a turbine. So we want, this is negative, so we want actually make each side the inverse. So minus HP plus this will give us equal to this magnitude. So this will be the energy that comes out of the system, which is going to be equal to the change in elevation and the head loss in the system. What have I done wrong? There's a sign convention wrong, right? This is upstream, so this is positive. This is negative. HP Z2 minus Z1 is equal to HP. It was negative before, right? Z2 is on this side. So let me get rid of that. So I don't know what this is. Oh, I didn't know that either. So this is going to be Z2 minus Z1, which is the way we have it. It's going to be plus this, and it's going to be equal to HP. And so this, in terms of, oh yeah, that's fine, of course. So we make it negative. I see what I'm doing. So we make this negative. HP is equal to Z1 minus Z2 minus HL. So this is the energy getting from the pump. It's equal to the difference in this. This is a positive value in terms of the energy we get out of it. It's not a power, but it's minus the head loss. So it's always going to work against the head loss. So there's going to be a loss in the pipe as a result of that. If we run it in the other mode, then in the nighttime mode, it's going to be this. It's going to be 2 and 1. It's also going to be HP. And if we write this, it's going to be, the only terms we have to deal with are going to be Z1 plus HP is equal to Z2 plus HL. So if we rearrange it, we are going to end up with HP is equal to Z2 minus Z1 plus HL. And so this magnitude here is going to be positive. So we have to provide, so this term here is Z1 minus Z2. This term is going to be positive, and so this is by definition, the amount of energy that we apply, and we're going to have to fight against frictional losses to be able to get it up to the top of the hill. So the bottom line is that whether we're generating power, we're working when it goes downhill against the head losses that act against that flow, which is what this case is here. This head loss always acts against this. And in the opposite mode, when we're pumping uphill, then we have to work against the head losses, which are against this. So it's the same, actually only making the case for this, is that each time I pull this bag across here, I use energy to get it from one point to the other. So friction always acts against motion. It always acts against to resist it. So the net loss in the system occurs in both directions as you either pump to get up to this upper reservoir or flow it through the turbine, and so the losses would be roughly the same if it's going through at the same velocities. And that's it. And so that's kind of the punchline, I think. I won't go through another one. So the punchline for today is that we'll only use the idea of conservation of energy in this kind of one-dimensional format. We'll do it from upstream to downstream in a single stream tube or a turbine, but essentially a linear system. Within that linear system, we have two new components. An amount of energy that we can put in, which we define either as this or as this. And intrinsically, when our viscosity is not equal to zero, we have losses within the system, which are kind of important in dealing with real-world systems, because that's what we have to work against in reality. So in dimensioning pumps to get fluids out of the ground, for example, then head losses are a real component that we have to deal with. So we can deal with it through Bernoulli's equation, written in this way, where we don't have any change of phase in the system. It's relatively straightforward. All we've done is add a loss term, an input term, and this non-uniform velocity of flow across the pipe, which is a number between 0 and 1, which we'll almost never use. And if we're dealing with a machine where there's a phase change, then it's convenient for us to take the pressure term and to add an internal energy term and define behavior in terms of enthalpy. And enthalpy is just defined as the internal energy per unit mass, and this is the pressure head term that go together. Usually enthalpy is a single number. It's measured in joules per kilogram, and if multiplied by a mass flow rate, it ends up being in watts. And this is the expression that we use between upstream and downstream when we have a phase change. And the only thing that really is important to remember is it now matters how you write it between upstream and downstream. It has to be upstream on this side and downstream on this side. And so it's actually because the directionality of these the pump terms, the input terms, and the loss terms actually matter. And so you just have to account for those, that sign convention. So that's it. Okay. All right. So we'll carry on with this next time. If you came in late, then apologies for the fact that we're in class this week. We just shifted the out-of-town week till later in the semester, till November sometime. So we'll carry on with this. Okay. Great. Thanks very much. Enjoy the great weather for now.